Hello, everyone. Welcome to our workshop. This is Gail with Benoit and Wu, whom you see on the side. So we are going to start the workshop now. We have, oops. This is the page of the GitHub repository that you will find at the address JuliaOcean Marine Ecosystems JuliaCon 2021.jl. I'm going to start today with a little introduction, and then we will dive in. So this workshop that we are going to present with myself, Gaël Forget, Benoit Pasquier, and Zhen Wu. You can find the materials online at this link on GitHub, as I said. This is a reminder of the YouTube stream. And for questions, we are going to use this pigeonhole framework. We will remind you of this as we go. So this workshop is motivated by the analysis and the science and the computational modeling having to do with marine ecosystems. So life in the oceans is strongly connected to our climate, as you know. And so this is sort of the broad theme of this workshop. This is also an opportunity to present and introduce you to the various modeling efforts that have been undertaken in the Julia Ocean and Julia Climate organization that we are all part of. And in the workshop, we will run a set of different models that range from individual microbes to processes that involve the entire planet. The schedule of the workshop is here. So I'm starting with this introduction, and then I will hand it over to Benoit, who will present a tutorial of the IBECS.jl package, followed by Wu, who will present Plankton Individuals, and then I will show you a couple of other packages afterwards. We will save time for questions after each of the presentations. The context for this workshop is, as I said, the connection and the simulation of marine ecosystems and climate. So one of the themes is the fact that there is a broad range of scales that are involved in this field, from the size of a marine microbe, which is maybe a micron in scale, to the entire planet, which is of the order of 10,000 of thousands of kilometers in scale. And in terms of time, we also have to cover a range that goes from seconds to millennia. So it's a very broad range to cover, and that leads to a hierarchy of modeling efforts. Another theme that you will encounter during this workshop time and time again is the notion of life in a moving fluid. The fact is that unlike on land, the motion of the fluid is a big part of what drives ecology. And then in this scientific field, there is a strong relations that exist between the physics, like the ocean currents, the chemistry, such as carbon, and biology. So it's a very interdisciplinary field. In the background also, there are many very important questions having to do with climate. And so the uptake of carbon is one of the things we'll talk about. the food web and biodiversity are also central to this this topic of discussion. So as I said, with this complex and multidimensional and high-dimensional problem, that is the simulation of marine ecosystems and climate, we look at typically a hierarchy of models. So we're going to show you a few of those today. They might range from a simple ODE that you run on a simple laptop to something that's much bigger. And over time, in this field, we've also used many different languages, Fortran being a predominant one, but also things like MATLAB and Python. But we're here today because we all collectively here consider that Julia is really the way forward, first to develop new models, but also to kind of unify the previous approaches. So we'll demonstrate that. Couple of pictures to illustrate what I just said. On the left is an illustration of what a plankton cell might look like in a simple, yet still simple model. It would be for one individual microbe. And on the right-hand side, you have this sense of the global scale. This plot shows the flux of carbon across the sea surface. So in this workshop, we will go from across this whole range and back and forth. I should mention before we move forward that a lot of this work happens in the context of the Julia Ocean and Julia Climate Organization. So if you want to get involved or after the workshop, if you want to ask questions or follow up with us, these are a good place to go. There are others, and we are very grateful to the entire Julia community, of course, of which our work benefits tremendously. In terms of funding, I will highlight at least NASA, sort of physical oceanography, the MAP, and the IDS programs that have supported some of what you're going to see and use today, and the Simons Foundation, which supports some of our work through the Sea Biomes Scope and Gradient programs. So concretely, this is how you can try the materials we prepared for the workshop. We are going to use Pluto notebooks. And so all you have to do, supposedly you already have installed Julia, is start it. Install Pluto if you don't have it. And then you can run a notebook in this fashion by saying using Pluto, and then Pluto run, and you put the address of the notebook. Another approach, which Benoit will showcase briefly, is to use Julia Hub, which allows you to, instead of using your own computer, fire an instance of Pluto notebooks or Pluto server in the cloud. So that's probably enough for the introduction. One thing that we have to remind you of is to go for questions, to go to this address, and this is the service that that we'll be using called Pigeonhole. So you go to pigeonhole.80/marine for this specific workshop, and we will be keeping an eye on questions as they come in. Right now, we don't have any. We will come back to this screen after the different presentations. Sorry, I was here. So there we go. And the other important information is this address. This is where you'll find the material for the different tutorials. We will try and put those banners on regularly as we go. And I think this is all I had to say up to now. So I'm going to turn it over to Benoit, who is going to tell us about IBECS.jl. So I'm going to share this. And there we go. I need to put myself on mute.
All right. Thank you, Gael, for the introduction. I'm Benoit. I'm a postdoc at USC, and I'm going to talk to you about IBECS.jl, which is a package to simulate marine tracers in a very simple and computationally inexpensive way. Just to follow up on what Gael said, to show you how to run those notebooks, this is the Julia Ocean organization page. You can click on the marine ecosystems JuliaCon repository. Gael showed you that. If you've started a Pluto page and you're used to that, you can paste the URL of the notebook here directly. So let me do that as an example. I will go into the SRC folder, take this tutorial for IBECS. You need, I believe, the raw version of it. I copy paste this link into the URL and I can start it that way. This is one of the ways you can do it. I'm going to close that and show you how to do it on Julia Hub. Same idea. Once you're on Julia Hub, you probably have to log in. I'm already logged in. You have to launch Pluto, choose a few of the settings for the CPU, GPU, whatever you want to run. In my case, I just need a CPU. Start the job. I think you get a few credits for free at the start. And then once it's started, you will have the same Pluto page and you can paste the same URL in there. Okay. So I could potentially connect once the instance has started up and run it from there. Okay, I will close that and go to the notebook that I already started in Pluto. The reason I started it is because it takes a few minutes to launch, and I didn't want to impose that to all you guys. So let me dive in now into my tutorial. IBECS.jl, as I said, is a package for simulating marine tracers in the global ocean at steady state, essentially. There are hopefully plans, if I can afford to work more on it, to extend it to do non-steady tracers. But for now, we're going to do only steady state tracers, and we're going to look at radiocarbon. Radiocarbon is, as you may know, a very useful isotope of carbon for dating things. It's got numerous applications that I'm not going to list here. And within the documentation of IBECS, there is a tutorial to simulate this radiocarbon, which looks like this. And I'm not going to go through it because this is a heavily inspired notebook from this tutorial, except it has a few more little nice little plotting plotted plots and interactive bits from Pluto. If you run this tutorial on your own for the first time, it will download some data and it might hit a few hiccups where you have to rerun some cells. So you just have to essentially press Shift Enter in a couple of cells, and then you should be all set and see all the plots and all the notebook display as it should. All right, that's out of the way. Now let's dive a little bit into the science and the context of this notebook. Radiocarbon is used to look at mixing and ventilation in the ocean. So how does it work? Radiocarbon is produced in the upper atmosphere by cosmic rays hitting nitrogen atoms. This radiocarbon, which is an isotope of carbon that's radioactive and that decays with a very long half-life of about 6,000 years. This radiocarbon reacts with oxygen, creates radioactive CO2, which is shown here, and some of it enters the ocean. Once it's in the ocean, there's no more source of this radiocarbon, and it decays. And so the ratio and the concentration difference as it is transported is going to change. And it's going to track a bit like a clock the age of the water mass that it's in. And eventually it's going to come back out again. And so this is what we are going to simulate as fast as we can in this short tutorial. Here is a plot of a simulated radiocarbon age. This is a horizontal map. There's some sliders that I can move around to look at the age, which goes blue for very old and goes to yellowish white colors for very young age. And I can examine it at different depths. This is a plot that we're going to make as we go through the tutorial. And you can, if you're running this locally, you can select, thanks to Pluto's reactivity, you can select latitude and longitude, and you will see a profile here on the right, a depth profile of where you clicked, and then some other plots will also react to where this location is. So how do we do that? This is using a simulated tracer for radiocarbon, and we use IBECS to simulate this tracer. And as Chris Rakokas likes to say, there's differential equations everywhere. There is one here for simulating radiocarbon. I don't want to go too much into the details. It's not a very complicated equation, but it's a typical tracer equation, and I will come back to it. So I will go through these terms here. R is radiocarbon concentration in the ocean. It depends on location, X, Y, and Z, and that's its rate of change at any point in the ocean. The first term here that follows is the circulation effect on concentration, which depends on the mean currents and the eddies and mixing, and all this is captured by this term here. On the right-hand side, you have two terms, one for the source of radiocarbon in the ocean, which is due to air-sea gas exchange, so that's this term, which has piston velocity over a certain length scale, and it's represented here. And the radiocarbon concentration is sort of returned to the atmospheric concentration, or the atmospheric partial pressure. And the last term here is the radioactive decay from the natural behavior of radiocarbon. This equation is a continuous three-dimensional PDE. It's way too complicated to solve by hand, so we use simulations. And for that, we discretize the ocean. This is not the model that we're going to use, but you could imagine a very simplistic 2 by 2 by 2 box model of the ocean. And in IBECS in particular, we linearize or vectorize the whole 3D assemblage by just doing what's illustrated by this little animation. We just collect all the boxes into one big vector, and we operate on vectors and set up the problem in a matrix framework, which allows us to use linear algebra, solvers, and all of the suite of cool things we can do with linear algebra. The tracer equation itself is sort of transformed in this discrete context and linearized context, but it looks pretty similar. It's reproduced here. We still have the rate of change, but we also have a much simpler term here for the circulation. we have just a big, large sparse matrix T, and the terms on the right are unchanged. And we are going to look for the steady state of this equation. That is, we want to cancel this term here. Now let's dive into the actual computation. We're going to use IBECS. Like any Julia package, you have to type using the name of the package. So here, this is handled by Pluto's package management. I just need to write using IBECS, and it will know how to go download it. You do need the latest version 0.15, I think, of Pluto for this to work on its own. Once this is done, we're going to load circulation. So it's some data that's somewhere on the internet that is going to be downloaded. If it's the first time that you run this notebook, it's going to use AIBECS.jl to download the data. Otherwise, it's just going to read a file that's on your laptop or on your local machine. And in this case, we are loading the OCA matrix and circulation, which was made by Gael, who's our presenter that you heard just before. It's based on the MITgcm and other observations, so it's an estimate of the circulation. But again, essentially what we are grabbing is a transport matrix, a large sparse matrix, and some grid information that we're going to use to do our simulation. This here might be one of those cells that you have to run twice. That's that warning here. One thing we'll do later, we will come back here and change that matrix and circulation and see how it changes the whole results and the output and the plots. The grid is just a very exhaustive object of all the details of the three-dimensional grid with latitude, longitude, depth, and other elements that can be useful for computation. And they come from an extra package that's sort of part of the ecosystem of IBECS. The matrix T here is this sparse matrix I've been talking about. In this case, it's not huge, but it's fairly big. It's 84,000 by 84,000 with 500,000 non-zeros, structural non-zeros. And you can see the sparsity pattern. You can see there's a structure, but it's not a structure that fits into any of Julia's customized matrix types. So it is just a sparse matrix. Now that we have the transport matrix, we need to provide IBECS with the terms that were on the right-hand side, which were the piston velocity exchange of radiocarbon with the atmosphere and the decay. So that's that function here. In IBECS, you always have to provide the local sources and sinks. So you provide the transport, the circulation, and the local sources and sinks. We also need an extra term here for the depth of all the boxes, because this expression here for the exchange depends, with the atmosphere, depends on depth. Only the top layer or the top layers of the model will exchange radiocarbon with the atmosphere. So that's what this term here does, and we need this Z here. And there's some function in IBECS which returns the vector of all the depths of all the grid box. So that's this big vector of all the depths. A few things that you might have noticed here in this function is that I used two arguments. R is radiocarbon concentration, and P is model parameters, which I unpacked here thanks to the unpack.jl package, which simply takes, it provides a macro to elegantly unpack elements from a struct or type or any other, or many other types of objects, Julia objects. So I need to build a struct for these parameters. That's the interface that I use for IBECS. In this case, I use one of the, what is it called? The meta field, I forgot what is metadata fields, I think, .jl, which allows me to add some metadata to each of the entries of my struct. And in this case, I use the units macro from that package that is re-exported by IBEX, so that I can, avoid to think too much about unit conversions, which is a very common source of mistakes in climate sciences and ocean sciences. So I use unitful under the hood, unitful.jl, which is a really cool Julia tool, if you don't know about it, to deal with units and do conversions on the fly at very low cost. And so this is the struct for my parameters. There's the 4 parameters: piston velocity, length scale over which the exchange with the atmosphere happens, decay time scale, and atmospheric concentration. Once I have my type, I can instantiate a P object using this type. So this is what I do here. And this is the table of parameters. This is dealt with under the hood by IBEX to print out a data frame. But it's just a nice way to see what parameters you have for your model and units. And you can add other metadata that might be useful, like a description or a distribution, a prior distribution, a range of reasonable values, or anything you want, actually. So now we have everything. We have the transport, the right-hand side terms, the sources and sinks, and we can solve the problem. Before we solve the problem, there's one last step that IBEX will handle for you, is that we need to create a function for the rate of change. So that's just a function that under the hood is going to reassemble your transport matrix and your right-hand side to create this rate of change function that depends on the radiocarbon concentration and the parameters. And it's also going to spit out a Jacobian that is built using fordiv.jl under the hood, and some knowledge that we have of the sparsity pattern of this Jacobian. It's not using the more recent tools from SciML yet, but hopefully in the future it will use that. For now, it just cumbersomely reassembles the Jacobian under the hood, but you don't have to worry about it. This is all done here. And this is what this f and del subscript xf are. So it's the state function, the rate of change, and its Jacobian. Once we have those, we can then directly solve for the rate of change equal to 0, which is the steady state of the system, by applying Newton's method for root finding. And for that, we use a solver that is in IBEX, but is derived from C.T. Kelly MATLAB algorithms. I will come back to that in a few lines. We have to give an initial guess for the radiocarbon concentrations. Here I just choose a bunch of zeros. It shouldn't matter too much. Sometimes it matters. Here it doesn't matter because it's a very simple model. Once that is done, I'm all ready to create my steady state problem following the SciML lingo and sort of trying to keep using the same tools over all the Julia packages. So I'm trying to eventually port or delegate some of this functionality to SciML eventually. So this is why I'm using the same sort of lingo. And once this is done, I solve that problem using this CTK alg, which is part of IBEX that I mentioned earlier. But hopefully this eventually will be able to replace it by any solver that's available in Julia, in Optim or NLsolvers.jl, or from CT Kelly's coming algorithms. Hopefully will be all packaged in nonlinear solve.jl, which I think is getting there, but I don't think it was there when I prepared this notebook. So at this stage, you'll have to use this if you want to run this notebook. And that's it. That solve takes about 7 seconds. I don't know if you can see with the resolution. I can actually rerun it and see how long it takes. It takes a little less because that was the second run. So it's about 2 seconds. but it depends on the grid, on the resolution, on the circulation, and so on and so forth. Once we've solved for radiocarbon, the last step is to convert this radiocarbon concentration into carbon age, radiocarbon age. So if we assume that it starts at an atmospheric value and decays exponentially with the time scale of the parameters, we can rearrange this equation and get back at the time since last contact with the surface, which is this formula here, and I apply that, convert it to seconds and then to years using unitful again to get a nice vector here of all the values of all the ages within the ocean. Okay, that was a bit of a painful scroll down of small cells of code, but we're done. We have the radiocarbon age in a vector, and using plots, we have some recipes that are available from IBECS to plot things and plot this tracer. So that's the tracer of radiocarbon age, which is called here with plot horizontal slice of the radiocarbon age, given the grid information and some depth level, which is controlled by this slider. So if I move this slider around, you can see the map change. And that's essentially it for this tutorial. There's a few things I'm going to go through now, which are sort of prettier plots and different angles. And so in order to do that, I'm going to go back up and bring down this main plot, which allows me to select different locations. And I'm here. Okay. All right, so here this is the exact same plot that I just shown earlier, except this one has a bit of an extra control. As I was saying, you can select different locations. And so if I go below, I have another example plot, which is a typical plot that we look at in oceanography, which is a meridional slice. So we take this longitude, this meridian, and along that meridian, we take a slice. So that's what you're seeing here. If I move around here in the Indian Ocean, you have a different slice. If I move around here, you'll have an Atlantic slice, and it's really an efficient way to explore what's going on. For example, here for the sciencey part, you can see young waters, so sort of yellowish colors coming from the north. So that's, I should have explained that that's depth on the y-axis and that's latitude on the right axis. So you have South Pole, North Pole. You have cold, dense waters coming from the North Pacific that sink quickly and bring young waters in the deep. That's the typical thing you do in oceanography, is look at these tracers and try to understand where things go, where things come from, and how long it took. And you can see that it took quite a couple of years, at least for this inference from radiocarbon. We can, of course, look at profiles. This is what we see here. So that's the depth profile at that location. So it should be the next plot here. If I move my location around, you see that the profile here changes. It's the same as this one. And again, you can look at the details of this tracer through all these recipes that offer different lenses to look at your simulations, which I find really useful for exploration, and I think could be really useful for teaching, and that I use for my research. All right, this is it for the main tutorial. I will, depending on time, go through this. I will check with Gael. Maybe I should stop for questions.
I think it's up to you. You have a little bit more time now. There's a couple of questions on Pigeonhole. Maybe you take them at 5 minutes.
I will leave the I will leave this part out, and I will come back to it later if I need to. I will go have a look at the questions. The problem is I put my questions in the same panel, so let me do this. Okay. Which Julia, first question, there's only 2 questions, so I'll go quickly. Which Julia plotting package is being used? It's plots.jl. It's because at the time I started, it was the most used package, and writing recipes for it was surprisingly simple. And so there's only recipes for the plots package. But there are some functions to, regardless of the plotting package, to rearrange slices and different diagnostics and profiles that you can then feed to any plotting package fairly easily. For instance, when I do research with IBECS, I tend to prefer to use Mackie for better looking plots that are more better quality in general, I believe, and easier to customize. And that's exactly what I do. I hope that answers the question. The other question is that there's a failure to precompile IBECS. So that's going to be hard for me to answer. I can see some comments. I would need more information. I think it might be a netcdf problem. These are the only questions. So we can either take a break or pass it on to Wu.
I thought you had a little extra stuff you wanted maybe to show.
If I have the time, I can do that. I can do that for sure.
The other thing is, I was going to ask you if you wanted to maybe say a little more about the other kind of applications and examples for IBECS that you have, I believe, in your documentation.
Absolutely. All right, let's look at that. So in the documentation, there's a bunch of tutorials which are essentially different examples of different tracers and different functions between them, and more simple and complex examples. So if I go to the documentation, which looks like this, on the left-hand side, you have all those tutorials. This is Radiocarbon in this case, but there's other examples. Ideal age is sort of an idealized version of what we just looked at, which is probably a better way to look at time since contact with the atmosphere. There's an example coupling 2 tracers, because real ocean tracers generally interact with each other. And so this is another example, and it's a bit more complicated because it's non-linear and there are 2 tracers. And then there's a bunch of extra tools in IBECS to do these simulations. For instance, I'm particularly in my work currently interested in trace metals. So we look at ways to deliver those metals to our ocean models. So there's data for dust deposition from atmospheric models that we can use. And there's a river discharge data set that we can use for injecting nutrients at the river mouths, and same thing with groundwater. There's a bunch of other things in the documentation, which I think I shouldn't go through all of it. But anything you would like to simulate fairly quickly, to either for research or for teaching, get in contact, and I will be happy to help you try and get it running in an interactive notebook or for research in a script. Or I hope this answers your question. And I'm sorry if I sound a bit tired. It's 1 a.m. for me, talking from Sydney.
No, I think this was great. Thank you, Benoit, so much. It's yeah, tough time zone you're in. So thanks for being with us today.
Thank you, guys.
So, yeah. So maybe let's see, where were we? In the schedule, I think next is going to be Wu, who's going to tell us about PlanktonIndividuals.jl. Are you ready?
Yes, but I saw some questions popped up on Pigeonhole. Maybe Benoit can answer questions first, and then I can go.
I see. He took a couple of them already.
Yeah, there's some new questions.
Oh, okay. Benoit, do you want to go back?
I will take a look. All right, I'm obviously not in the right spot. I am having trouble seeing the questions for some reasons.
They're on the screen that I'm sharing right now.
Oh yeah, okay. No, I just needed to update my page for some reason. There's a question about floods in Germany and Europe. Absolutely not. IBEX is not capable of predicting floods. IBEX uses an established, fixed, prescribed circulation of the ocean. There is probably much better tools to investigate floods. This is really to simulate long-term climatological tracers in the ocean, and there's no way to, within IBEX, look at changes of the circulation itself. And so predicting floods and surges and storm surges and things like that is absolutely not a capability of IBEX. There's another question which says I can select location on the main plot, but I couldn't select the radiocarbon age to change the meridional slice. So I think maybe there was some confusion there. The only place where you can select meridian and a longitude is on the main plot, where you point that crossbar, that latitude longitude, that sets the latitude and the longitude. So I hope that's it. That answers that question, and that's it for the questions.
Okay, so thanks, and I'm Zheng Wu, postdoc at MIT, and today I'm going to introduce PlanktonIndividuals.jl, which is individual-based phytoplankton life cycle model written in Julia and can run on both CPU and GPU. The model simulates the life cycle of ocean phytoplankton cells as Lagrangian particles, and all the nutrients like phosphate, nitrogen are represented as Eulerian tracers, and all these tracers and particles are advected over the graded domain. So here the plot, as Gail showed just now, it illustrates all the processes, physiological processes described in the model in the phytoplankton cell. And you can see the cell can absorb light and fix carbon, and it will uptake inorganic nutrients, and it will build biomass, and the cell will divide if it's grow if it grow big enough, and it will be grazed or naturally dead. Here's the full documentation here. And this documentation includes all the all the equations described in to describe the physiological processes like photosynthesis rate, nutrient uptake rates. I will not go into details for the equations, but we will go through for the whole parts, like photosynthesis, nutrient uptake, and we have excretion and biosynthesis, and also chlorophyll synthesis. And the cell division is a probability of cell size and time. So these are for the phytoplankton cells, and for the biogeochemistry we have like carbon cycle here, nitrogen cycle, and the phosphorus cycle. These tracers are Eulerian tracers, and the Eulerian tracers will interact with particles. Individual phytoplankton individuals will interact between each other. And one more I would like to mention in this documentation is the benchmark on GPU. So because in the ocean there's millions of microbes, so it's useful to have GPU support because it can run like fast and can support like more particles. I run in different scenarios to check the benchmarks on CPU and the GPU, and you can see on on zero-dimensional model, the speed up for CPU from GPU to CPU is like 20 or less than 20 times, and for two-dimensional models, which includes the advection of Eulerian tracers, it's still a lot. Like this one to this one, it's more. And for three-dimensional models, it's even more, like 35 times. Wait a second. Yes, so 60 milliseconds and 590 milliseconds, the comparison. Okay, let's back to the tutorial. So here, what I would like to show is an example to simulate a vertical slice of the ocean. And this animation illustrates the particles, like the phytoplankton particles, moving around according to the velocity fields, and the Eulerian tracers also is also advected by the flow fields. So first, in order to get this animation, we need to using two packages. The first one is PlanktonIndividuals.jl, and the second one is for plotting is plots.jl. And we also need to include a script, hyperfunctions.jl, which is in the examples folder in the PlanktonIndividuals.jl. It helps to generate the flow fields used here. After we load all these packages, we need to specify the architecture we would like to run on, and the grid we would like to run. So here we choose to use CPU, and the grid we are using regular rectilinear grids, and it's 128 by 128 grid boxes with 1 meter thick and 1 meter wide. So it's like a two-dimensional grid box. And the topology is periodic around X and Y, and bounded for the vertical direction. And we use a stream function to generate the flow field. The flow field looks like this. And after we got the grid information, we need to set up the individual-based model, and the function is here. So we use Plankton model, this constructor, to generate the model. First, we need to specify the architecture and the grid, and after that, we need to specify how many species you want to simulate in this simulation. Now we just simulate one species of phytoplankton cells, and you need to specify the initial numbers of individuals you want to have. For now, it's like 2 to the 7th. And because of the GPU, we need the GPU prefer to pre-allocate all the arrays at first, and won't want to change the size of the array. So because individuals will grow and divide, so we set a maximum number of individuals the model can hold. It's like 8 times of the initial number. After the model is generated, we include it in the Plankton simulation, which will specify the time step and the number of time steps. And we also include the flow fields generated by the stream function. The delta t velocity here specify the time step of velocity, which means the time step of velocity can be different from the time step of Plankton model. It means you can use like for one time step of velocity for multiple time steps of Plankton model. And after you generate simulation, you update it, and then you can plot this plot here. And in order to generate the animation I showed just now, we use the code below, and it's slightly different from what we have here, because in order to generate the animation, we need to stop the model every time step to plot and to collect all the plots together to get the animation. So here the time step, the number of time step is 1. So the simulation will stop every time step, and here we use a for loop to iterate the simulation. And in this way, we can get this animation. And for these functions here, we have like detailed explanations in the documentation, like this one. So we have Plankton models. We just used, we need to specify architecture, we need to specify grades, and we need to specify species, the number of individuals, and the maximum number of individuals. And we can also specify different parameters for these individuals. And this is one of the exercises, I think. Yeah. And for the simulation, I just used here is like we need to include the model, we need to include time step, number of time steps, and we can also specify like the PAR, the photosynthetically active radiation, and the temperature. And we can also include diagnostics to get outputs like the growth rate, division, the growth rate, photosynthesis rate, etc. So that's I think that's the two main functions we need to use to run the model. And here are some exercises. So first one is really simple to add like the second species, and we can do it now, like here. We can just change this number to 2 and run the cell. Then we can see 2 species in this plot. And here for the animation, it's the same. We can see like 2 species moving around. It may take some time. Wait a second, it freezed. Okay, yeah, got it. So we have two species together moving around, and for the animation, you will see these particles moving around according to the velocity fields. And another thing I would like to mention is, freeze. Oh, yes. So now if you don't want to change the parameters, you can just have like two species together, because each species needs its own set of parameters. And if you want to add the second or the third or more species, you need to provide their the parameter set for the second, for the third or fourth species, and the instructions are listed here. You can check. And the second exercise is to run for a longer period. We can also see, like here, we just need to change the number of time steps to like 4 hours. So it's 240. And then the model will run for 2 hours, for 4 hours. And for the delta t velocity, you will also need to change it, because you need to use the velocity, the same velocity field for the whole time period. So the velocity fields will be, oh, sorry, it's just a freeze. Will be like, yes. So that's the first and the second exercise. Okay, yeah, and the third exercise is, I think it's more interesting, because we want to run the model because we would like to see the diagnostics, because for example, growth rate, division rate, mortality rates, or how these individuals distribute along the vertical gradient, vertical profile, something like that. So we need to add diagnostics to the model to export the outputs. So here we use Plankton Diagnostics, the constructor, to generate the holder for diagnostics. First, we need to include model, and we need to specify which tracer we are interested. So for now, it's like PAR, ammonia, nitrate, and the dissolved organic carbon. And that's for the Eulerian tracers. We use tracers for that. And for plankton, we are interested in the number of individuals. We are interested in the grazing rate, mortality rate, and the division rate. So we use this for diagnostics. And the frequency means how many time steps to get the average of the number of time steps of the model. So you can, so for 1 means you get diagnostics every time step. If there's is 10 or 20, it means you get the diagnostics of the every 20 time steps. You get the average of that. And then you need to include diagnostics in the plankton simulation here to actually let the diagnostics run in the simulation. And you need to specify where you want to put the diagnostics in the in which direction you want to put it. Yes, I think that's for the model. And let's see, we got the, yes, we got the 2 species together running around. Yeah. So any questions, or am I too quick?
Yeah, I think there's a couple of questions on that came up. Let me share my screen.
Yep. Oh yes, predator-prey dynamics. Yes, yeah, that's a really interesting question, and that's what I'm working on now, because you need to have an encounter rate from phytoplankton from zooplankton to phytoplankton. So that's a bit difficult for now, and currently I'm just using a quadratic grazing term. So it's not actually included, but it will be in the future. And yes, and for 2-dimensional or 3-dimensional models, I think just the quadratic grading term will be different from the 0-dimensional model. Yeah, another question about predators. Yes, we are working on that, but not for now, because each individual represents like millions of cells, and that's not actually grazer and phytoplankton. It's like super grazer and super phytoplankton. So there should be some parameterization in there. So still working on that. But for the interactions besides grazing, there's also other interactions like self-shading. If there's some more individuals in the surface, then the light will not come in. So that's a kind of interaction.
Can I ask one also?
Yeah, sure.
I guess make a suggestion that you maybe you want to. Can you say a bit more about the sort of the complementarity between the kind of Eulerian modeling perspective that happens on a grid, which I believe you use for tracers, and the sort of Lagrangian frame modeling, which happens following the individuals. Do you want to comment a bit on that?
Yeah, sure, of course. I mean, so usually we like most of the biogeochemical models we treat phytoplanktons as Eulerian tracers, and the reason we built this model is that we think there's some like heterogeneity within one grid. For phytoplankton cells, there should be like a distribution of cell size and the distribution of different rates, because each cell is different. And also another reason for this model is we would like to include more physiological processes for each phytoplankton cell, and it will be difficult to treat different reserves as Eulerian tracers and still treat this, like if you graze on one cell, the cell will be grazed. But if you graze on like different Eulerian tracers of C and P, then it's like a bit hard to describe to describe. Yeah. Thanks, Gail.
Well, thank you. This was great. I learned a lot about this every time you present it. Do you want to say more on your exercises, or do you want me to take over? What do you think?
Yeah, maybe if I have time, I would like to show some more examples, but like here. So yeah, besides the yeah, besides the regular rectilinear grids, we also have like regular latitude, longitude grids, which we support the simulation of a regional or global setup. So like here, so we are simulating particles in the global ocean. That should be like interesting to see the distributions of different regions, and yeah. Also, for the diagnostics, I'm illustrating it in a single zero-dimensional model. Like if we include diagnostics here, like we are interested in these tracers, in these attributes of phytoplankton, then we can plot like this, like the division rate, like the population division rate, mortality rate, and photosynthesis rate, which are, I think makes more sense for the biologists or for the scientists. Yeah.
Can you maybe also briefly mention the packages that you are relying on in Plankton Individuals that might be of interest to the audience?
Sorry, what?
Like your dependencies, which packages do you use from the Julia ecosystem?
Ah, yes, that's more interesting, I think. Let me see. Let me show here. So basically, because we have GPU support, then we need CUDA, of course, here. And besides that, what we need is like
maybe zoom in a little.
Oh yeah, sure. Yeah, we use kernel abstractions for the programming on both GPU and CPU. And besides that, I think I just need random to generate random numbers. And I use struct array to store all the attributes for phytoplankton because it's worked perfectly on CPU and GPU together. That should be the main package I depend on. Yes.
Great, thanks for that. I think there's a couple of new questions for you to look at also.
Okay, let me see. Which one?
There is one about, are you able to estimate the impact of more sour pH and more CO2 on planktons?
For now, no, but it's easily to simulate that because I just need to include one or two more Eulerian tracer as like the pH and the CO2 in the model, and include the RC flux to get that. I think that's what I need to do to simulate that, but that's not hard. And we also have a package for RC fluxes, and we can just use that for that. Yeah. And the next one is what types of starting conditions lead to bloom type of responses in your model? Okay, you mean algae bloom, algal bloom, something like that? Actually, for now, for all these examples, we are using a really low concentrations for nutrients, so there's not a bloom. There's not a bloom in these examples, but if you increase the nutrient concentrations, there should be a bloom because they are not the cells are not limited by the nutrients. Am I answering your question? No.
I think you did. In other ways, maybe to say it, it's kind of a new modeling framework, and there's still a lot to explore in the parameter range, and maybe you haven't quite experimented with that specific. Oh, yeah.
Yeah.
One more came in.
Yeah. I haven't checked the modeling toolkit. Maybe I should check that and see if I can.
Excellent.
Yeah, maybe for modeling toolkit, I think that because I mean, I have lots of physiological processes like all these equations. Maybe it's a bit hard to include all these things in modeling toolkit. But I'll check and see if we can do that. If it's more get higher performance, we would like to do that, of course.
Yeah, maybe I feel it would be a good kind of test case for the team that develops modeling toolkit to see if if the framework can easily accommodate the sort of the blend of Eulerian gridded Lagrangian ODE type components that you have.
Yeah.
Cool.
Okay. Oh, okay, I see the comments. Modeling toolkit might be a little early for this. Okay, thanks. Thanks for the explanation.
This was great. Thank you, Wu.
Thank you.
Okay,
so I think maybe
shall we take a break before before you start?
Yeah.
I think 3-minute break, something like that.
Yeah. Do you want to?
I'll do it.
We have a video for that. So we're back. All right, so welcome back, everybody. So we had so far 2 great presentations by Benoit on IBECS, which is a framework to do sort of global simulation at long time scales and looking at equilibria over the global ocean, for example. And then we had another great presentation by Wu about Plankton individuals, which is rather on the sort of local interactions within an ecosystem, and is kind of more of a Lagrangian framework in a sense, an agent-based model. So we sort of seen two sort of end members of what a hierarchy of models aimed at analyzing marine ecosystems and their relation to climate may look like. In the next 40 minutes or so, I will show you something similar, looking at kind of those two different perspectives. So I will start with a presentation on MITgcmTools.jl, which is a package that leverages a widely used climate model, ocean model primarily. And then I will tell you about individual displacements, which is more like what Wu was describing in some way, and is pure Julia. So let me start with this one. So this first presentation, so again, it's a notebook that you will find in our repository, which is available in GitHub. This is one that you can run in different frameworks, on different platforms locally. It will require a Fortran compiler though, so sometimes it's easier to maybe use a cloud computing service like Julia Hub or mybinder.org, which I believe should provide a working solution to this. So I've run the notebook locally, and I'm going to walk you through that after telling you a little bit more about what the framework is that I'm using. So as I said before, this is leveraging a pre-existing model that in fact is written in Fortran. It's called the MIT General Circulation Model. And specifically, I'm going to be using one of its tutorial, which is linked here. I open this over here. So this is the experiment from this model that we are going to be running from within Julia. It works on a global grid, and it simulates the fate and behavior of the biogeochemical ocean where marine ecosystems are represented in a kind of a parametric way. So these are the equations being solved for the biochemistry. This resembles what Benoit was showing you for radiocarbon, except it has a slightly different set of equations that relate carbon to alkalinity and nutrients that feed into the marine ecosystem and the food web. And so here there is more explanation about this framework. Typically, it produces maps like this, which show the RC fluxes of carbon. This is for the kind of the pre-industrial case, so before humans introduce a bunch more carbon. And in the notebook, we will change that parameter and see a little bit what it does to the ocean. Before I move on, I should say that MITgcm is one of those sort of climate models and ocean models that have been widely used and are the result of a long investment in terms of research and development. And so here you see that it goes back to 1998. It's still being developed actively. The lead developer is Jean-Michel Campin, and a lot of us, including myself, have contributed to this model. So this has a fairly wide community of users, and one of the idea of what I'm doing is to try and connect that community with the Julia community. And so this leads me back to this notebook. So what we are going to do here is use a couple of Julia packages that I've been developing that are called MITgcmTools, which provides a kind of an interface to the MITgcm Fortran code, and Climate Models, which is sort of an abstraction layer on top of that that I will also present later during the week at JuliaCon as a lightning talk. The other packages that are used in this notebook are just Pluto AI for a bit of interactivity and plots.jl. So the way that this is going to proceed is we're going to use MITgcm from within Julia. We're going to compile it. The workflow is going to be something that looks like this. We have a setup method, which is provided by PlanktonModels.jl, a build method, and a launch method. And that's really all there is to it. So the goal here is to take those sort of complicated to build, sometimes fortran-based models that are widely used, and provide a simple high-level interface to the via Julia that now we can use to demonstrate and to rely on, exploit those modeling frameworks in a nice and easy way through live demos like this, for example. What should I say? So the basic idea is to have a model, a data structure, which is the model configuration, which is shown here, which has, upon the setup method, been associated with a unique identifier and a folder to work in. And then the model is going to build automatically. It's going to then run and puts it output in this folder. And then on top of this, it's going to provide a Git record of the workflow. So I'm going to illustrate that in practice. So here is, I started the notebook a little earlier, and so I did the beginning part of it already. This is an example of a simulation of 3 years. The initial run in the notebook is just a few time steps. So this one I've extended, and you're going to see that in a second. This is part of the notebook. Now this runs for 3 years, and you're seeing the mean carbon concentration in the ocean as a function of time. And in this case, it's sort of oscillates with the signal cycle, and it kind of goes down. Here is the recording of the workflow up to this point. So this corresponds to 3 different model runs, in fact. The initial one that was very short was this part. This is the first step where I changed a few things in the way that the model output is being generated. And this is the third one where I've extended the duration. So this corresponds to these first 2 cells in the notebook as you look down that say modify and rerun. this one, and that one. This third one I haven't done yet. So this is the one where I'm going to uncomment this and launch it. Once this is complete, we will see updates to this, which will have more information, and the plot will be updated. That's the beauty of using Pluto as an interface. I can leverage this reactivity. As this proceeds, this gives me a little more time to tell you about, I think it might take about 10 minutes, to tell you about the way that we interact with MITgcm2 files. So a lot of these climate models, they have a bunch of parameters, and they are typically provided in text files. So within MITgcmTools.jl and via PlanktonModels.jl, I provide a way to interact with this. So here we read them in within Julia. We change this this parameter, which is the concentration of carbon in the atmosphere. This new value corresponds to a concentration, a level that is after we've already injected us collectively a bunch of carbon in the atmosphere through using cars and so on. And then we write it back to file. There is this little function that I use, git log fill, to write down in the git log that is part of the run folder that we just changed this. And then we call again the same set of 3 methods, clean, which will remove the previous run directory, setup, which will put it back in place to initiate a new model run, and then launch, which will run the model effectively. And at the end of this, I also copy the standard output from the model to keep track of each model run and put that in the Git record. So this is still running. So I'm going to show you a little bit inside of the folders. Creating this here. So now you're looking at a terminal window, and I am in this folder that was created along the way. Run is what is going to contain all of the model output. And so here you see, for example, this file being created, these files. And they get created every minute or two, depends. Here I'm running the model in a serial fashion. So this is not the most efficient I could do, but this is the way it comes out with the notebook. So I don't need MPI. MITgcm otherwise runs multi-threaded and on multiple processors. So here you see a new one as a plan. So it's running. If I go into the log folder, this is where I've been keeping track of what's happening. And so what was depicted on the screen really was those Git messages that I've been inserting in this folder. So for example, the change in the parameter file, I'll show you this. This is where I increase the number of time step original. So the idea of this support of Git provided by Git and via ClimateModels.jl is that it will allow for keeping track of your workflows and making your sometimes iterative trial and error type of things better documented and reproducible. So that's one of the components that's added by ClimateModels.jl. So this is a good time to show you a little bit of the documentation of that package. So ClimateModels.jl provides this interface that I've described which essentially provide functions with this setup, build, and launch methods that can apply in a very general fashion to kind of any climate modeling framework that I've ever seen. Excuse me. It provides this tracked workflow framework via Git to favor and help you with creating reproducible workflows. And then there's another component, which is this sort of replay mode, where instead of rerunning models, we can leverage output previously generated and that might be stored in the cloud, on the internet, or somewhere. There is a list of examples here to show you that this framework can be applied equally and equally simply to a Julia function or Julia package. This is a Julia package. This is the case of a Julia function, where we just do a kind of a random walk like this, just coded in Julia. This will be used in this one in the next tutorial that I'm going to present, which involves running a kind of a model for ocean turbulence, if you like. Although it's a bit of oversimplification, but I'm saying it this way. Written entirely in Julia by Milan Clover. This is the case of using MITgcm again, but now in an atmospheric simulation. And then in this one, I've also done tracking of particles in Julia. This is an atmospheric model called PD.F90, which is another Fortran model. And then this is the case of using sort of cloud computing to retrieve model output and do sort of climate science type of analysis. Here we're just computing temperatures. So let me go back to my tutorial. Somehow it's still running. Oh wow! Must have a few other things running on my laptop right now. Let's see. Ooh, like that. Okay, should be about done. So once it's done, this plot will update. What we have done in this latest experiment is change the atmospheric concentration of CO2 to represent a case where climate has been modified by us. And so this curve, instead of sort of being flat or going down, should be going up. The record of the workflow that you see here, which starts with run 2, will be updated with a part having to do with run 3, which is what I'm doing now. I've already shown you this. This is it.
But while it's running, maybe you can answer. There's a question that popped up. I'll read it to you. Have you thought about connecting your models with the MIMI.jl ecosystem, which focuses on calculating the social cost of carbon?
Yeah, so there is, it's a very good question. There's a set of different packages and frameworks in Julia that this climate models.jl could play with, and MIMI.jl is definitely one of them. There is other kind of climate models also, but on my short list of test cases, I think MIMI.jl should be featured for sure. And I have not digged very deeply into it yet, but that's a very good question. Thanks for that. All right. I should have compiled with MPI, I think.
Well, since it's still running, I'll ask a question. the Git log that you have, not Git log, but the Git handled log that you keep of all the workflow. It's reminiscent a bit of a package that I haven't used much, but I've seen in talks, which is drwatson.jl, which you know about. Could you tell us a bit if you've compared them, and if you have any comments on the? I think it has a similar feature, but I'm not sure. But maybe it does.
Yeah, I'm not entirely sure myself, but I do believe that it uses Git also in a similar way. Here, this is really sort of much more directed toward a specific task, which is to sort of monitor the way that we interact with these models, and the size, I would say, of climate models is fairly small, sort of on purpose, because I kind of want it to be easily maintainable and to kind of have a low-level control on those things that anybody will be able to understand. So that's why I went with just using Git directly rather than leveraging a more complex package on that. In addition, I've sort of followed the same logic in a way with file supports. So I'm kind of trying to use, I think I'm using netcdf.jl. I'm using csv.jl. Let me show you that. Where was that? So in my dependencies, what you will find is that it's pretty basic. It's pretty low level. So I'm using things like netcdf directly, toml, git. Data frames is one of the more complex packages that I'm using, I guess. But I sort of favored using rather low-level packages in a sense, rather than more elaborated ones that would already combine these type of things. I'm sorry. Cool. All right. So now that my model run has finished, I can illustrate what I was saying. Now you see this increase in the carbon over this time period, which is 3 years, give or take. So this is the effect of changing the parameter in the model that prescribes the atmospheric concentration. And we could have plotted other things, such as the way that anomaly in carbon in the atmosphere sort of projects inside the ocean. Kept things relatively simple in this notebook. And as I said, and as we were talking about before, this change in parameter and new run has been reflected in the record, the Git record. So I think that's all that I was going to say on this tutorial. Maybe I can have a look at see if there is more questions on it. Doesn't seem to be the case. Okay. So then maybe I'll move on to the other one.
Before you do so, can I ask another question?
Sure, please do.
For a user, a newbie user that would like to run a MITgcm simulation, to explore the effect of climate change, how long does it take to run say, the next 100 years or the next 300 years to explore things like that using the tools that you've built?
Yeah, thanks for that question. This is a very good one. It very much depends on the answer. Very much depends on the configuration that you use, right? And so in this case, what is being used is a kind of a coarse resolution model with a half-day timestamp. If you put, when I tried earlier, this run that I just did in 10-15 minutes, in fact, only took 5 before. So I think it's reflective of the fact that I'm running something else on my laptop, that it went slow like that. Then you can speed that up by also using MPI. Here I just use 1 core, but I could have used 4, which would have sped up the computation by maybe a factor of 4. Sometimes the bottleneck becomes communication. But that's for this particular configuration. So I think, I was saying 5 minutes for 3 years with 1 core. So if we make it, 1 minute for 3 years with 4 cores, maybe we're doing 100 years in what now, 30 minutes. Now, it's also a very interesting question because we use MITgcm and these kind of models at much higher resolution, right? And so, for example, we could do the same thing with a 1 kilometer mesh instead of here a 200 kilometer resolution mesh. So all of a sudden, we're talking about something that is orders of magnitude bigger. So we are now going to be using not my laptop, but a supercomputer. And then communication might be a bigger issue at that point because we're going to make different choices. And the other big piece of that is once you increase the resolution, the time step is going to drop, right? So when we run at the kilometer scale, the time step, instead of being half a day, maybe this was 6 hours, but anyway, turns into like 10 seconds. And so at that point, we're going to have something that takes a lot longer. Now, today I'm using Pluto and I'm doing this interactively, right? And that's one of the beauties of Pluto is that I'm able to make live demos and sort of shine this sort of new light on sort of older models. But the other type of workflow that you're going to proceed with when it gets more computationally expensive is you're going to go to a bigger cluster or a supercomputer. I'm using the NASA ones often. And then you're going to use a queuing system. And so that's why the method is called launch, not just run. And this is part of what I mean to support with ClimateModels.jl as well. These sort of workflows that will take longer, but you just have to wait for the output and then you can proceed and iterate. All right.
Thank you. Thank you for your answer. Great answer.
All right. So then, unless something else came on here, nope, good. So then I'm going to proceed with the other tutorial that I have. So this one sort of goes back to what Wu was describing in terms of following particles. And instead of making a model simulation on a grid, doing it in this sort of Lagrangian framework. So while Wu in his presentation and his package is doing that sort of internally, I've also been developing a package which is called IndividualDisplacements.jl, which is meant to be a more general framework, maybe less targeted, to do this regardless of model configuration. So often we are going to have data. Here, I think I'm showing in the bottom panel. This is actual observations of instruments that we put at sea. And this framework called IndividualDisplacements.jl will let you sort of simulate what this data set look like based on a previous estimate or model output for the flow field. So this is what's shown, for example, in this top plot here. This is a package that I've published with the Journal of Open Source Software this year. And so it has kind of two examples here. The one at the bottom is what I just described. Here I simulated what's called a drifting float, although in a simplified manner. So you have kind of the trajectories on the left-hand side that show you some particle going along the Gulf Stream and then kind of back southward. And it follows, in this case, just the three-dimensional flow field. So it goes up in the water column and then back down along trajectory. And then on top of that, it measures temperature and salinity along the way, which is shown on the right-hand side. So here you have, I think, 4 years, 4 different seasonal cycles. But the same package now can also be applied to, in this top plot, an atmospheric simulation, a simplified one, I should say. And so here it's a lot more turbulent. We're looking at the so-called health and stress benchmark, which is often used for dynamical cores in atmospheric models. And so that's the purpose of this IndividualDisplacements.jl package, to support this sort of applications across a range of models and across a range of parameters. So this is the documentation of this package. And you will see that there is several examples, some that I've already touched on. These are sort of more idealized one. You're looking at a kind of a two-dimensional case for a small domain with a randomly generated flow field. And so what the package does ultimately is just use those fields and compute, displace little dots on the map, compute trajectories, if you like, in this space. Here is a case that's sort of even simpler of just solid body rotation, but when you modify it slightly, you get something that is in fact an interesting case for ocean science, which is this sort of spiral, this kind of spiral pattern. And then in addition, there's also this sort of global ocean case and this sort of three-dimensional pathway. So here I'm looking at the North Pacific in a region where we're very interested in the way that marine ecosystems behave, the way that they are impacted by marine heat waves. And this is meant to look at the connection sort of from the two sides of Hawaii. For today, going back to the tutorial, I'm going to use a shallow water equation model that's been developed by Milan Clover. And so what this package provides is a simulation of turbulent flow fields that you see here depicted. And you might know that Milan is a lot better with graphics than I am. So this is the sort of flow fields that is particularly also relevant to the understanding of marine ecosystems, because along those complicated and time evolving flows. A lot of processes take a marine ecosystem and kind of stretch it. This also favors the way that the different species might interact in across space. This is a horizontal plane, by the way. So for this tutorial, which you will find as before in our GitHub repository, I'm going to be using this flow field computed in Julia, in pure Julia, by the shadowwaters.jl package. And you might start recognizing things that I showed in the previous presentation that was using the same sort of high-level interface called ClimateModels.jl with a fortran model. So again, I've encapsulated the workflow within this high-level framework, which means that I'm creating a run folder automatically and a record of the workflow automatically. Here is the definition of the model configuration, which is a data structure that's depicted just above. It has some input parameters for the number of points in the first direction, the number of points in the second direction, and then the size of the domain. That's going to be parameters for shadowwaters.jl. And then for the part having to do with IndividualDisplacements.jl, there's going to be this number of particles that are going to be simulated. So when you experiment with this tutorial, which is a Pluto notebook, you can change all of those parameters and rerun everything. Then the ClimateModels.jl framework proceeds as before. It has a setup, it has a build, which in this case, because everything is in Julia, is empty. But having it makes for a very general framework. And then call the launch method. Upon calling the launch method, everything gets generated, stored into files, and then we can do the plotting at the end. So this is a depiction of the flow field as it evolves through time. The colors in the background are just a kind of a tracer, a dye, that's initialized with this checkerboard pattern for illustrating the way that the flow field is happening. This is something that I took from Milan, in fact. And then you see the dots that are coming out of IndividualDisplacements.jl on top of that. The packages that have been used in this example, as I said, shadowwaters.jl, IndividualDisplacements.jl, and ClimateModels.jl. Those are the main three. Plots is what I used for the plotting in this case. And then this is for files, This is just not super important. And this is data frames, which is the way that the output from IndividualDisplacements.jl is stored. In doing this, what was provided to ClimateModels.jl was this function, which is the top level. And so here you see that this function gets in the model config data structure. It then runs the shadowwater model, rereads the output from file. This is the setup of the individual displacements data structure, which is called individuals. And then this is the time loop that is going to integrate over the Lagrangian component to simulate the trajectories. So there are other packages in the Julia ecosystem that compute trajectories. This one is the one that is sort of targeted towards ocean and climate and atmospheric simulations that I've described. Finally, here we take the output from that model, put in a CSV file. So this is sort of the type of workflows that we might do in analyzing marine ecosystems, as well as the physics of the atmosphere and the ocean. It's just encapsulated in this one function, passed to the higher level interface that PlanktonModels.jl. A few other functions are included at the bottom of the notebook that you can look at. This is to run the shadowweathers.jl. This is to just reread the NetEDF files that were generated by the shadowweathers.jl package. This is just for loops, and this is the plotting function. So the plotting function, as you will see, is pretty straightforward. It rereads the data frame, it rereads NetEDF files, and then overlays the heat map and a scatter plot. It is called in this loop via a macro here to generate a movie. Here. So this is a feature from the plots.jl package. You can do similar things with other plotting packages like Mackie.jl. Generated in this case here, we're generating a GIF. So this is what I had on this notebook. I think I have explained all that I had in mind. So I'm going to head over to the questions, see if there are any. Doesn't seem to be the case. Seems that I have gone a little fast on this.
I have a question for both you and Wu. What's the connection between individual displacements and individual planktons? Can they be combined? Are they combined by default? Do I need to do any work? Can I replace the little dots we were seeing embedded in these shallow water simulations? Can I replace those dots by little planktons?
Well, I can start. Maybe we'll add to that. So right now, the two computations are done independently. But one thing that's been on my list is to, on my to-do list, I should say, is to drive, sort of like you just imagined, to drive the plankton individuals via or using individual displacements for the computation of trajectories. That's something we just haven't done yet. One of the reasons that I think Wu went in recorded or coded independently the sort of this particle tracking part is to have a low level control and be able to use the GPUs. So that's something that IndividualDisplacements.jl is not really trying to support, at least not yet. And the dependencies that I have could make that complicated, in fact. So that's one reason to kind of have it set up independently in the first place. But then there are other scenarios that I think are quite interesting, especially from the perspective of modeling marine ecosystems, which is, for example, I can compute a set of trajectories within a global model, maybe a biochemistry model like the one that I illustrated in the previous tutorial, or the one that you can run with IBECS. And then on those trajectories, embed one of Wu's model to turn that into kind of a framework to do what people sometimes call aquacosms, where you are, in one of my trajectories, are carrying an entire ecosystem, if you like, right? That starts to interact with sort of the globe. So I think those two things are kind of bound to happen. They are of interest to myself, I think to Wu also. and then we will see where things go from there.
Yes, Gail's right, because I mean, I need GPU support, so I recoded all these things independently. So, and for now, for in Plankton Individuals, it has like advection schemes, and it has like biogeochemical cycles, but really simple one, and it has also has like a individual-based model, which includes all the physiological processes. So that's like 3 parts. And yes, Gil's right. So we are working together to see if we can like using individual displacement as a input, like the trajectories from individual displacement as an input for Plankton individuals, because like Plankton individuals are focusing on like small scales, and a trajectory from the global model, like a water parcel from global model, can be a really whole ecosystem in Plankton individuals, and we can see from that how these phytoplankton cells travel and act to the environment changes. Yes.
Yeah, no, thanks for that question. Yeah. One more, I guess, piece of answer to that is that individual displacements is also meant as kind of an analysis framework that can ingest trajectories that either have been observed at sea or have been computed by a different model, like Plankton individuals, or MITgcm, in fact, which also has kind of a Lagrangian module in it. Just to add to that. All right, I think we are kind of early on time. I'm looking at questions. I think there's a couple of people typing, so I'll wait on that. So for those who maybe weren't with us at the beginning, this is a summary page of what we've talked about. A set of different packages and tutorials that are available for you in GitHub. So this is the link that I'm adding on the screen now, where you will find all of those tutorials. We have talked about IBECS.jl, which is a framework to look at the long time scales and kind of the global problems. We've talked about PlanktonIndividuals.jl, which is a framework to look at sort of the more local interaction between within a marine ecosystem and between different types of plankton, for example. And then I've presented a couple of other notebooks that use slightly different technologies, complementary ones in many ways, that either rely on flow fields computed by and simulations computed by a widely used general circulation model called the MITgcm. And we looked at the way that carbon that the world has added to the atmosphere since the industrial era might project into the ocean and be stored in the ocean. This goes back, in fact, to this sort of very long time scales, potentially, because the volume of the ocean is so big, right? But it's also of concern to climate change over the coming decades and centuries. And then in this last tutorial, sort of went back to more local considerations in terms of shorter time scales, maybe, and the way that a marine ecosystem might be affected by a turbulent flow field, which in the ocean is a huge and very important component. the fact that we have those so-called mesoscale features and sub-mesoscale features. And so these are often well understood through particle tracking and so-called Lagrangian frameworks such as PlanktonIndividuals and IndividualDisplacements.jl. Before going back to questions, I should also say that this is a set of packages that are developed by a community and for the community at large in the context of the Julia Ocean and Julia Climate organization. So I would encourage you to follow us there and to get involved in if you are interested in this kind of topics and modeling efforts. The issue trackers are always a good way to do that on GitHub. So if there's questions that maybe you haven't gotten around to ask today, or maybe you're watching this in kind of at a better time than on a Sunday in the future, please reach out to us and, for example, contact us on GitHub. Emails are also obviously welcome. And then there is a lot of other frameworks that the Julia community has used and is using to discuss this sort of community efforts. So there is a discourse website, and there's also a Slack channel, for example, that we will be monitoring and can be used. Take a look at the question. We have a new one. So this is a little bit what I was describing about how to get involved. So we certainly welcome people that have used different languages. Python is mentioned in this question. Yeah, so this is exciting to hear that people want to get involved with us. A good place to orient regarding contribution. That's something that, at least me personally, I need to do a better job at, in a sense. So I intend to sort of clarify that on the GitHub repositories of the different packages. So maybe the simplest answer as of now is keep an eye on those GitHub repositories and don't hesitate to reach out afterwards. Benoit and Wu, maybe you want to say something?
Yeah, I was going to say, I think a good place to start is to just run the tutorials, go through them of whichever package you're interested in, and then explore from those tutorials some ideas, some things you want to try, and usually you will stumble on some things either you don't understand or that are not well explained or that just don't work, and then you start an issue, and then if you're motivated enough to contribute to the actual code, I think that's the best way, so that it's something you've tried and you sort of know already a bit and you're interested in. I think this is better than, for example, say being directed a bit blindly to try and work on something that you might not be interested in the end. So yeah, I think try the packages for yourself. Think of things you would like to do with them that are maybe not available yet, and start with issues on GitHub. I think that's probably the best way. Certainly not the only way.
Yeah, I totally agree with Benoit, and like starting with tutorials and examples on GitHub, and maybe open up issues or pull requests, for example, to see if you have questions or want to I find some bugs or something, etc. Yeah.
Cool. Great. So a couple more questions that came in. Can climate models interface with other climate models, example, FABM? So yes, that's kind of one of the goals, is to build a build a library of climate models and make them easily available for experimentation through the same interface. I have not worked specifically on FABM, but I have kind of a list of different models that I'm working on to sort of extend what's already available. And so there's a simple kind of climate model called Hector that I've looked at. There's something called also ISCA, which is developed out of University of Exeter, I believe. And a couple other ones that are sort of like-minded in the way that they are relatively low-dimensional with relatively simple interfaces, sometimes written in Python or directly in Fortran, that are on my list. Then there is sort of the bigger climate models. And the idea there is, I have the expertise for MITgcm, so I did that one. But I'm going to be looking for members of the community that knows best some of those other climate models to help me write the interface, right? So one of the goals is, if the experts of each model sort of sit and work on that, that's the one-time effort of making the interface, then everybody else can start using them much more easily. So I think it's a win-win, and I'm hoping people will jump in to contribute on that. Thanks for that question. I'm going to write this one inside that one. I was trying to run the last individual displacements model and it crashed as I ran out of space in TMP. How much space do you need to run? Good question. So it sort of depends on the parameters. I don't have a trace of that, so I don't have a very definitive answer. But I would say try and change the number of particles to start with. So that was in this notebook, right? So if you reduce that number to 100, this should take less space. Now, one thing I can look at is what the output looked like in my folder here. Oops, not the right window. So this current run that I did did generate 500 megabytes of output for the positions, and it did generate from the shallow water model something like 50 megabytes. So to run this specific example, you probably need around 700 megabytes. There are ways in individual displacements to change the frequency of the output. Maybe that's a little big. I'll try to work on reducing that in the GitHub repository. So if you keep an eye on that, I'll try to reduce it, because this is a little bigger than I thought it was. Thank you for that question. All right. All right. I guess we'll wait a little more to see if questions are coming in. Benoit, I'm very happy to see that you're still awake, despite the fact that it's like 2:15 a.m. in Australia. Do you want to add anything to the discussion or jump in some way? You don't have to.
This is tough. This is pretty tough at this stage. I'm falling asleep, and it's not related to the excellent quality of your presentation. It's just that I'm tired. But I think there's a new question coming in. I don't know if you spotted it. Oh, actually, no, that's just me being tired. I see someone is typing, but I don't see the question yet. So maybe it's not good. No, thank you very much for all the presentations and organizing. I learned a bunch of things today. There's a bunch of things I would like to look at now. So thank you.
Yeah, it's my pleasure, and thank you for being so reactive and enthusiastic about this, and sticking with us on the Sunday night.
You're confused. It's Monday morning.
Yes, exactly. Yeah, it's one of those. I guess the Sunday schedule is an interesting one. It's the first time that I do a seminar on type tutorial on a Sunday. I'm very glad for the audience being here on that level. So thank you all. I think a new question did come in. Yeah, so that's a very good question, having to do with sort of some of the goals of what I'm doing, and I think what we are doing collectively. So the question is, in what ways can you modify your models based on real data? For example, in the question, using track buoys to modify individual displacements model or measure solute concentration of plankton. So the answer is that there is sort of many different frameworks that can be leveraged to that end. In fact, a lot of my work in the past has had to do with this sort of questions, where we use, say, general circulation models like the MITgcm, and we write an interface to data to make a direct comparison between the two. From that point, we work on making that comparison quantitative. So we write what's called a cost function. And then we can run some sort of optimization of our model parameters. So that would be something that's kind of on the horizon with a lot of the Julia packages we use. And one of the reasons that I'm so excited to work with Julia now is that it has a lot of the sort of technology that we need to do this already sort of in the making, already well advanced, in fact. So we're talking about things like automatic differentiation to compute the sort of the gradient of a model data distance. The presentation of on modeling toolkit yesterday had some of that. There's going to be another discussion of this, I think, tomorrow. There's a workshop on AD, automatic differentiation. So that's one of the tools that is kind of well suited to do this sort of parameter estimation, model optimization based on data. And in fact, one of the reasons that I'm so involved with the MITgcm is that it also has, despite being in Fortran, support for automatic differentiation. So we've done this ocean state estimation type of efforts using MITgcm in the past. Now, there is a lot of other technologies, and one thing that I might mention is I've been recently involved with a project where we took, and this is with the Ocean Cleanup project, led by Axel Petava in the Workwise, where we used a different approach, which is called the ensemble Kalman filter in a Python framework in this case, to combine a Lagrangian simulation with simulated data, in this case, of plastic concentrations. So we have those sort of this experience that's building in terms of combining Lagrangian and Eulerian data sets, models and data sets. And a third component, that you can think of is machine learning, neural networks, and so on, which is another reason to be excited with the Julia ecosystem that has a lot of that already sort of built-in or building up. So I think there's many ways that that I'm hoping to apply and use some of those models that we've developed and discussed today in combination with data to do kind of optimization. So on the individual displacements, for example, one of the sort of obvious candidate in my mind is the sort of the stochastic component that you can add to the simulation of Lagrangian trajectories, and then optimize based on data potentially. See,
there's a follow-up.
Yeah. If you see it on the screen, yeah. What statistical methods would you use to determine if a specific modification is appropriate? Well, there's various candidates to that. I'm not necessarily going to extend myself in answering that in too many details because that's not necessarily my specialty. But there's like simple ones that involve just basically least squares and being within the range of specified uncertainties. So I like to think of this a little bit in the sense of, once you have kind of a balanced distribution of adjustments and misfits, whether amongst your parameters and your data, that the probability density functions and so on are as expected or as sort of specified a priori. That's one aspect. But it's a sort of a long question to answer.
I would like to jump in here. I think there's also some potential with some other packages that we haven't mentioned so far, like Turing.jl for Bayesian inference, and in an ideal, fully implemented ecosystem of packages, maybe a few years from now, we will be able to do that. I hope that kind of stuff where we take some data and we can estimate the likelihood of the parameters and optimal parameter choices and sensitivities in a really well-posed Bayesian framework. And that would have to rely on some metrics, of course, of like sums of squares of mismatches and some weights, and there's always going to be a bit of arbitrary choices there. But yeah, I think there is some potential to do really cool statistical inference in the future with combining all these packages, auto-differentiation, Bayesian statistics, and climate, plankton models. Yeah.
Yeah, no, absolutely. Thanks for bringing up the Bayesian methods, which somehow I had overlooked.
But I don't think any of us, maybe Wu has thought about it. I've thought about trying to do something like that for IBEX types of models for a long time, but I just haven't had the time to connect those bits, and I don't know if it's easy or it's going to take a long time. So we'll have to see. But maybe I'm sure that in the future we will have some model come up with a nice link with something like Turing. Yeah. I think you're muted, Gail. That's okay.
There was a follow-up about the list of models that I'm exploring, so we can learn more about them. So I will. I kind of have that list in a slide on my ClimateModels.jl presentation at the end of next on Friday. So maybe I'll save that answer for that, and then it will, that list will evolve. So I will post that on the GitHub repository also sometime soon, probably this week. But yeah, there's Hector. That's one of them. There is anyway. I'm going to forget right now. I'm sort of tired, so I'd rather not try to do the list just yet. Thank you. Oh, we've done that one. Okay. So I think I'm not seeing any more questions coming in. They're sort of half hour early, but we don't necessarily have to extend all the way to the end. So we'll give another sort of 5 minutes, maybe, for people to ask a last-minute question. I haven't looked at the YouTube thread in a while, so we'll take a look at that. All right. So let's just give it another 5 minutes, and that gives me another chance to thank you both, Benoit and Wu, for doing this on a Sunday with me. Thanks to the audience for being here and asking all of those questions. This was awesome. And to the Julia community at large for developing all of these great packages that we are benefiting from tremendously. I guess I would like to say as a general comment that I've been involved with the Julia community for a few years now. And it's been a lovely experience. There's a lot of great people in there. And so not only do I think that I benefit a lot from the package environment that exists, the package ecosystem, I should say. But it's also been a pleasure, and I look forward to continuing that. I don't know if Wu or Benoit wants to sort of make final comments.
And we should also thank you, Gail, to make this happen.
Yeah, no worries.
Yes, thank you, Gail, for leading the Julia Ocean organization activities, this workshop, the previous workshops, and bringing us together. Thank you.
Awesome. You're welcome. All right. I am not seeing any more activity on Pigeonhole, which worked well. In fact, for us, it was nice. For the streaming, we use StreamYard, which I guess was my first time using it, and also very nice. So since there's no more activity, I say we adjourn and say goodbye, and see you all soon.
See you soon.
Bye-bye.